Swayam Prabha. Digital India. Educated India.
Welcome to Concrete Technology Module 2. Module 2 deals with aggregates. Module 2 deals with aggregates, and today in the lecture 1 we shall be looking into requirements of aggregates, petrographic classification, effect of size, shape and texture. So, let us see what is requirements of aggregates. Basically, if you recall, when we looked at concrete, concrete consists of cement paste matrix, if I may say so, with aggregate particles embedded in the cement paste matrix. And in normal concrete, the aggregates which actually forms the skeleton is about 65 to 70%, and paste is the rest of it. So, this 65 to 70% is a large quantity. It occupies the major volume of concrete in normal concrete. Right. Now, therefore, why you call it aggregate? Because aggregation of solid particles other than paste. So, aggregation of solid particle other than paste, and that is what we call as aggregates. This is essentially aggregation of solid particles, and that is what we call as aggregate. And one major important property is that it must be inert, and obviously since large quantity is used, it must be inexpensive. It must be inexpensive. Natural aggregates are formed due to process of weathering, and artificial ones are obtained by crushing larger parent mass. Well, I would not call it, these are called crushed aggregates, actually second one. So, you can have natural aggregates, that means natural gravels or natural sand, those forms are natural aggregates as they are available, and they are formed by the weathering action on rocks, parent rocks, and then the other source of aggregate other than natural ones, naturally available ones, are the crushed aggregates. Now, artificial aggregates can be produced from some materials like let us say fly ash. Now, these artificial aggregates are of course a separate class of material used for specific purpose, but largely what we use in normal concrete, normal strength concrete, and even in high strength concrete, they are either they are obtained by crushing rocks, or they are naturally available material like pebbles, gravels and sand, etc. Recycled aggregates of course is a recent concept, because of, you see, the aggregate resources are not infinite. Aggregate resources are not infinite. More and more aggregates are consumed in the concrete, the resources is getting reduced. So, there is now a thought process of utilizing recycled aggregate. There is another aspect also. There is a significant amount of demolition of existing structure, concrete structure may occur in future. So, when you demolish a structure, you get the demolition waste, similarly construction waste. So, can they be reprocessed in some manner, processed and recycle them for use in concrete again. This is being looked into, and therefore, recycled concrete aggregate is a recent concept. Chemical and mineralogical composition are important. Porosity, strength, hardness, thermal properties all have their origin in the parent rock. So, the chemical and mineralogical composition, porosity, strength, hardness, thermal properties, it all depends upon the parent rock itself, parent rock itself. Size, shape and surface structure, these are independent of parent rock, but play a major role in concrete. Size, shape and surface structure. So, thermal properties of concrete, the porosity, chemical composition, mineralogical composition, they will be same as the original parent rock itself. But once you make them, get them into appropriate size after crushing, or if it is natural, so in itself the shape and the size, they have very strong role, and surface structure of course, a very strong role in concrete. Well, they do not have definite shape, and sizes are expressed in terms of square sieve size. You do not have definite shapes. So, you will talk in terms of some sort of qualitative or linguistic terms such as rounded, etcetera, etcetera. They do not have definite geometrical shape. Size also varies. So, their sizes are defined in terms of square sieve size. So, you have sieve, square sieves, and these sizes are what we talk about, the square sieve side length. So, sieve size we talk about. So, size is related to sieve size. So, basically we do what is called sieve analysis, allow it to pass through square meshes or sieves, and series of them, normally a series of sieves should be there, and they are conveniently, then the aggregate size is conveniently described in terms of size of the opening. So, we do sieve analysis and conveniently relate the size of the aggregate to the size of the mesh, square mesh or sieve size as we call it. Quotient of linear dimension of opening of a given sieve to that of next larger size. Actually, you see the sieve sizes, many things in nature actually vary, do not vary linearly. For example, sizes of these particles, if you talk in terms of some sort of equivalent diameter, or through the sieve analysis you find out the size, you will find that the sizes varies over a large range. For example, might vary from something like 0.75 millimeter or 0.075 millimeter, that is 75 micron size, to 40 mm or 100 mm or 150 mm, or let us say in a given concrete it might vary 75 micron to something like 20 millimeter. Now, the range is micron, means 10 to the power minus 6 meter, millimeter is 10 to the power minus 3 meter. So, you can see the variation, the size varies, or the range of size is more than 1000 or nearly 1000 or more. So, such a large range, it is convenient to express in terms of log sizes. So, is the case with frequency of let us say mechanical waves or many waves, frequency of waves, there also we express them in terms of in logarithmic scale. So, here the sieve sizes we express them in logarithmic scale in geometric progression rather than in arithmetic progression. Because the range is large, it is convenient to express them in geometric progression, that is, if I have a size x, next size will be 2x, next to next size will be. So, it is x, 2x, 4x, etcetera, right, 4x, 8x and so on. Well, this 2, the quotient therefore is 2. So, quotient of linear dimension of opening of a given side to that of next larger size, this quotient of linear dimension, this actually we keep constant, and most often we use this quotient is 2 as 2. So, it is convenient to express the size of particles or aggregate particles in terms in geometric progression, and the quotient size quotient is generally used is 2, although it could have been anything else, but this is most convenient to use, and that is what we have been using. Well, therefore, if I have a 10 millimeter maximum size of aggregate, nominal maximum size of aggregate means majority of the aggregate will be passing through a 10 millimeter size mesh. So, square mesh. So, 10 mm, 10 mm, 10 mm. So, when I say that nominal maximum size of aggregate is MSA, aggregate is 10 millimeter, or abbreviated as MSA, maximum size of aggregate as 10 millimeter. Now onwards I will be talking of MSA and may not be stating this maximum size of aggregate all the time. So, if we understand that this is MSA is equals to 10 millimeter, it refers that most of the particle passing through square sieve size opening of 10 millimeter, most of it, a few small percentage might be retained, and this has come from practice. How much percentage can be retained is it comes from practice or are given in codes as we understand. Usually in normal structural concrete, MSA ranges up to 40 millimeter. So, in normal structural concrete, MSA ranges up to 40 millimeter, mostly 20 millimeter, and we will see of course, what it depends on, the choice of MSA depends on. Now, then we carry out sieve analysis in continuous series of sieves, and they are reported in terms of percentage passing or retained against sieve size. So, it is in a tabular form usually, it is in a tabular form usually, for example, 20 mm, size 10 mm, etcetera, and percentage passing. So, maybe 99% passing through this if the MSA is 20 mm, maybe 50% or 60 or 70% passing through this, etcetera. So, this is how we express. So, we do sieve analysis, sieves are placed one over another, a series of them, sieves are placed one over another, a series of them, put the material up and then shake it, so that the particles finer than the sieve size will pass downward to the next sieve, and some amount will be retained here. So, I can then measure the weights, the masses retained from a known mass. So, percentage retained or passing, etcetera, I can find out, and sieve analysis is done and results are expressed in this form. Adjectives such as fine or coarse aggregate indicate relative mean size. Fine aggregates has got a smaller relative mean size, right, smaller relative mean size. Combined aggregate are obtained by mixing two or more aggregate, usually one finer than other. So, we combine, for example, fine aggregate and coarse aggregate both are mixed together, we can mix them together and we get combined aggregate, and then combined aggregate is obtained by mixing in definite proportion, usually one fine, one the coarse. Well, the aggregate passing through 4.75 mm sieve size is important, and up to 0.075 millimeter, that is 75 micron, we call this as fine aggregate. We call this as fine aggregate. We call this as fine aggregate, and aggregate retained on 4.75, sizes higher larger than that, we call them coarse aggregate. Sand by and large belongs to above size range. You know, normal sand belongs to this size, that is natural sand that is available belongs to this size, and it often serves as fine aggregate. Natural sand belongs to the size greater than 0.075 millimeter up to 0.75 mm, and it serves as fine aggregate. Clay, silt and clay are finer than this size, as you know. And sand, of course, results from natural disintegration and abrasion of rocks. Sand results from disintegration, natural disintegration by wind, rain, etc., and abrasion of rock. Groups of rocks such as silica minerals, quartz, opal, tridymite, etc., these are the groups. So, classification on the basis of petrography, that is mineralogical classification. So, petrographical classes can be in terms of minerals, for example, quartz, opal, feldspar, micaceous, carbonates, sulfates, etc., So, you can classify them in this kind of terms. Now, certain minerals have a little bit of problem, that is they are susceptible to what is known as alkali aggregate reaction, hence petrography is important. Because of the durability issue, petrography is important when an aggregate is used for the first time. If it is a proven aggregate, it has been used in many structures for and it did not exhibit sign of any deterioration or alkali aggregate reaction over many years, then of course, we are sure of it. But if an aggregate is used for the first time, not used before, then its petrography must be, or its mineralogical composition must be looked into, because some aggregates are susceptible to what is called alkali aggregate reaction. Recall, in the first slide itself I said that aggregate must be inert, it should not react. Now, certain types of silica, like this is one of them, certain types of silica such as opal, they can react with sodium, or sodium hydroxide, finally, of course, in presence of water, and form a kind of gel, This gel absorbs water and increases in volume. And this expansion in hardened concrete can cause cracking. We will look into this issue of alkali aggregate reaction in detail when we talk of durability of concrete. So, certain aggregates are prone to such durability problem and cause deterioration of concrete structure. So, petrographic analysis is very important, because you can then identify the mineralogical compositions, and the minerals if present in the aggregate can make the concrete susceptible to alkali aggregate reaction. So, you can see that aggregate having satisfactory service records can be compared with aggregate used for the first time to ensure suitability. If you are using it for the first time, that is where you got to look into their suitability. The one which have been used for long period of time, one need not bother about them. So, petrography is done in order to find out the mineralogical composition, type of minerals present, and to identify whether potentially alkali aggregate reactive minerals are present or not. Classification, petrographic classifications are based on the mineralogical composition. Like as I said, dolomite, maybe limestone, calcareous, siliceous, or that kind of nomenclature. So, they are important from alkali aggregate reaction point of view. If you know a particular type of mineral which is prone to alkali aggregate reaction, then that should be that particular aggregate should be tested more and possibly maybe isolated and not used in concrete construction. Shape is very important. Roundness measures the relative sharpness of the edges, relative sharpness of edges. So, if I have something like this has got fixed edges, sharp edges. So, roundness measures the relative sharpness of edges. Rounded aggregate has less sharp, rounded aggregate has got less sharp edge. For example, if this is rounded off, the sharp edge would vanish. So, this will be a rounded aggregate. Normally, natural aggregate will have tendency due to abrasion and weathering action, the sharp edges will vanish. So, other shape, the initial one was angular shape. So, rounded aggregate have less sharp edges compared to angular aggregate. So, initially it was angular aggregate, a rounded aggregate will have less sharp edges. Roundness is consequent of strength, abrasion resistance of parent rock and where it was subjected to. If it is a strong aggregate, it is likely to be less round because it may not get its edges may not it may still be there, and abrasion resistance is very important because the edges are they become rounded through abrasive action and wear and tear. So, therefore, how much wear it has undergone, it will depend upon that. A crushed aggregate obviously will have a tendency to remain angular. If you have crushed it, it will have a tendency to remain angular, right. Rounded aggregate, natural aggregate, through abrasion and wear and tear, it might lose its edges and therefore, it may be rounded. In case of crushed aggregate, nature of the parent rock, crusher type and reduction ratio governs the shape. So, it is the crusher type, parent aggregate of course, parent rock, crusher type and reduction ratio, how much, what size you are reducing to, all this will govern the shape. River gravels of course are rounded, while crushed rocks are angular. So, this is what we must understand. By and large, crushed rocks will be angular and river gravels should be rounded. Naturally available river sand is also rounded, whereas crushed stone, if powder, if I use stone dust, they will be likely to be angular in shape, because while crushing it will fail on the possible failure planes and it is unlikely that it will have a rounded shape. The crusher jaws, between the crusher jaws, it is crushed between crusher jaws. So, this it is unlikely that it will be rounded. So, crushed rocks are generally angular, crushed rocks are angular. Right. So, shape wise, if we look at the classification, rounded, this is one of the classifications, fully on, no original faces, that we call as rounded. River gravel, for example, it will be fully on, all wear out, no original faces. Angular, little evidence of wear, well defined edges, you get from crushed rocks. Now, there are in between, there are various shape classification, but we have just listed down a few here. Elongated are ones which has got length much greater than other dimensions. For example, this is an elongated aggregate, length greater than any other dimension, Flaky, length is greater than width, all right, length is greater than width, but it is very large compared to thickness. So, shape wise some classification we can do, very broad classification. There may be many more in between, subangular, etcetera, etcetera. Now, numerically, if we want to express some of this aspect related to shape, let us say A is the greatest length, maximum length, B is the intermediate length and C is the shortest length. So, we defined elongation ratio Q as B by A, elongated is this. So, this is my A, B is the intermediate, could be even slightly bigger than this, let us say B is something like this, right. B is something of this kind, all right. B is something of this kind, all right. B is something like this. So, B is this and C is the thickness, C is this, C is this. Then elongation ratio is B by A, flatness ratio is C by B, flatness ratio is C by B, right. Shape factor one can talk in terms of P by Q, that is flatness ratio divided by elongation ratio and AC by B square, AC by B square. Now, if it is elongated B by A, if this is small, that means this is elongated. If this is, if this is C is small compared to B, then it is flat, all right, it is flat. So, elongation ratio to flatness ratio gives you shape factor, It is one of the ways of quantifying shape. Codes, basically all codes will restrict use of flaky or elongated aggregates. So, codes actually restrict the use of flaky and elongated aggregates, because they would normally create planes of weaknesses when you put them together. So, flaky aggregates, if you put them together, set of flaky, one plate over another, they will tend to create weak joints in between, right. We want in fact random, the aggregate should be embedded in paste. Now, here there might be aggregate might be just over another aggregate and weak planes could be created. So, this flaky or elongated aggregates are not desirable, they are not desirable. A particle is flaky if thickness is 0.6 of mean arithmetic sieve size. If a particle is flaky if thickness is less than 0.6 of its mean arithmetic sieve size, arithmetic mean sieve size. Mean is calculated on the basis of arithmetic sieve size. So, just sieve size, if it is less than 0.6 of the mean sieve size, then this is, you call it flaky. If it is elongated, if the length is 1.8 times the mean sieve size. So, you allow it to pass through some sieve and find out its length, the longest dimension compared to the sieve size, and if it is more than 1.8, because it can still pass through as a vertical simple, vertically just it can pass through the sieve size. So, if the length is more than 1.8 times, then we call it elongated. Flaky is if its thickness is smaller than 0.6 of the sieve size, then so you measure the smallest dimension, that should not be less than 0.6 of the sieve size through which it has passed through, through which it has passed. So, that is what is flaky, and it's the code restricts their use. Shape, a different sieve size than those used for grading. Well, shape of course is defined in terms of, you have a different sieves than used for grading or sieve analysis. The sieve analysis that the sieves that we use for shakiness, finding out how much percentage is flaky, we use a different sieve than those used for gradings. Percentage flaky particles by mass of the sample is flakiness index. So, if I have percentage of flaky particle in the material expressed as percentage mass of the sample, then we call it, that is what is flakiness index. So, flakiness index is defined as the percentage of flaky particle by mass of the total sample. If it is less than 50, then it should be less than 50 or less than 35 depending upon the usage, should be less than 50 or less than 35 depending upon the usage. The code gives you this restriction. Percentage of elongated particle by mass of the sample is elongation index. So, flakiness index should be less than 50 or 35 depending upon the usage, codes tells you that way. Similarly, elongated particle, mass of elongated particle divided by the total mass expressed as percentage, we call it elongation index, and that is also restricted by code. Angularity number is defined as 67% minus solid volume in a vessel filled in standard manner. This is another definition trying to define the shape. You fill a container in 3 layer, pack it up in 3 layer, right, fill this container with aggregate in 3 layer, and original volume is known by, volume of the vessel is known by filling water, by it is measured by filling water. Then you find out the solid volume in the vessel. So, if the solid volume is known, because you know the mass of the aggregate that has gone in divided by the specific gravity of the aggregate, that will give you the solid volume. 67 minus the solid volume is angularity number, because rounded aggregate packs better. So, the 67 has come from there actually. It is expected that rounded aggregates will give you a packing quality of 67 when you choose specific sizes. So, these sizes are specified in the code, and the specifics, when you use specific size and pack it in a standard manner, you find out what is the volume of solid after packing, and that volume 67 minus that volume will give you angularity number. The size is generally in the narrow range of 20 to 14 mm or 14 to 10 mm etcetera, depending upon the code, so and purpose. So, various codes uses this angularity. ACI code, for example, ACI recommendation uses this angularity number. This is what the idea is. 67% represents the most rounded aggregate, and that is why the 67% was used. Sphericity is defined as a function of specific surface. Sphericity is defined in it is a function of specific surface. Let us see how it is defined. Well, I will come to this definition a little bit later, but for practical usage, in concrete mix proportioning, when I want to determine the concrete mix proportion, two shape classifications are used for simplicity. These are simply natural, rounded or crushed. Well, new, of course, some other codes use more than that, but some codes use simply two classification as rounded and crushed. So, from shape point of view, qualitatively we can talk in terms of simply rounded and crushed, or then there are many other classifications in between, subangular, angular, etcetera, etcetera. But quantification is possible in terms of volume diameter. For example, volume diameter is the diameter of a sphere having same volume as irregular particle. So, volume diameter of a particle of an aggregate is the diameter of a sphere having same volume. Now, if Vp is the volume of a single particle, and if I assume that I have a sphere having the same volume, then 1 by 6 pi t cube or d 0 v cube as we have defined here will be equals to V p, and therefore, volume diameter is given by this expression. This is V stands for volume. So, volume diameter is given by this expression. Surface diameter is the diameter of the sphere of same surface area as the irregular particle. Now, surface area of a sphere is pi d 0 s square. Pi d square is the surface area of a sphere. So, that must be equals to area, surface area of the particle. So, therefore, surface diameter is defined in this manner. So, if you have an irregular shaped particle, if you know its surface area divided by pi, and if you take root over of it, that gives you surface diameter. So, we can define diameters in this manner, surface diameter and volume diameter, and then specific surface diameter is the diameter of sphere of same surface area per unit volume as the irregular particle. So, this is called specific surface diameter. Now, you see we talked of specific surface earlier in connection with cement, and we were mentioning that surface area per unit mass or per unit volume is used as specific surface. In the context of aggregate, we will be talking in terms of surface area per unit volume as the specific surface. So, specific surface here we define in terms of surface area per unit volume. So, now you consider specific surface diameter. It is the diameter of sphere of same surface area per unit volume as the irregular particle. So, what you got to do is you got to know A p and V p. So, that is the specific surface. Now, this must be equals to, for a sphere, this is pi d square divided by volume 1 by 6 pi d cube. So, you can find that 6 by d cube. Okay, I think it is there in the next slide. So, let us look at it. It will be V p by A p by V p, and specific surface of a sphere would be pi d square divided by 1/6 pi d cube. So, is equals to simply 6 by d. So, this d will be equals to 6 V p by A p, right. Now, specific surface volume diameter was, what was volume diameter? Volume diameter, specific surface diameter, volume and surface area of particle. Let us say the same derivation is available here straight away. So, 6 by d 0 is the specific surface of a sphere, and specific surface of particle is this, and if you equate this, specific surface diameter will be 6 V p by A p, 6 V p by A p, right. So, this is how we can find out various diameters, and through this we define sphericity factor. So, that is related to the shape. So, it is the ratio of specific surface diameter to volume diameter. So, this is the ratio of specific surface diameter to volume diameter, that is the idea. It is the ratio of specific surface diameter to volume diameter, right. So, we have seen how we define volume diameter. Therefore, this is given by this formula. This is the specific surface diameter and this is the volume diameter, right, and 6 V p by A p and 6 V p by pi. So, this will be pi to the power 1/3 and 6 V p, this is 1/3, this was 1 minus 1/3. So, this will be 2/3, here also is 6 V p divided by A p. For sphere, V p is equals to 1 by 6 pi d 0 cube, A p is equals to pi d square, right. So, put these values here pi d 0 square and put this value here of V p 1 by 6 pi d 0 cube, this will come 1. So, sphericity factor xi is the ratio of specific surface diameter to volume diameter and is 1 for sphere. Let us see what happens if I have larger sizes, I mean more angular sizes. For angular particle, for cube of course, yeah. So, if we see for cube, volume is V p is a 0 cube, A p is 6 a square, and this will turn out to be 0.806, because if we go back to the formula, B p by A p. So, this was a cube for the cube 6 a cube or 6 a cube to the power 3 by 2. So, it will be 6 under root 6 V p pi to the power 1 by 3, and area is B p, and B p is simply a cube, 6 under root 6 a, and here a will be 6 a square, and if you finally calculate out, this turns out to be 0.806. Sphericity factor will come out to be 0.806. For tetrahedron, this value is 0.53. You can show it similarly for tetrahedron, this value is 0.53. So, angularity factor is 1 by xi is the reciprocal of sphericity factor. So, we define another term. This is how we can quantify shape in some manner. Angularity factor is the reciprocal of sphericity factor, right. It is a reciprocal of sphericity factor, and this increases with irregularity in shape or angular shapes. This is highly angular, this is highly angular, this is still angular. So, as the angularity increases, xi reduces, therefore, 1 by xi will increase. For sphere, this value is 1, for angular shape, this value is more than 1, angularity factor is more than 1, angularity factor is more than 1. This is important because more angular the shape is, its packing density is poor, means when you pack these particles together, there will be large void left in them, and thus it results in more paste that to be used in the concrete to fill in those voids. So, that is why this is important. This will be very clear as we go further. The values of angularity factor may be 1.1, values of angularity factor may be 1.1, 1.1 for rounded aggregate. Rounded aggregate, it could be 1.1 for rounded aggregate, it could be rounded aggregate, it could be 1.1, right. So, it could be rounded, for rounded aggregate may be 1.1, and for irregular 1.4, and crushed aggregate 1.7. For crushed aggregate it is 1.7. The main important issue is the void content of aggregate is linearly related to angularity factor. This is the most important issue, that this is linearly related to angularity factor, and if you plot this graph, it has been observed that void content increases with aggregate, void content increases with aggregate, void content increases with aggregate, and it is like this, void content increases with aggregate. So, angularity factor increases, that means it is now more angular in shape, and void content increases as the angularity factor increases. So, that is why the shape is important. Now, more the voids, more would be the paste required to fill in the voids, and that is why the shape is very, very important in case of concrete, and that is why you are looking at shape. The size has got a role also, we shall check that role of the size, size also we will look into. So, size has got a role, Spherical particle specs to higher packing density compared to irregular shapes, right. Irregular shaped particle, and natural aggregates are seldom spheres. They are not spheres essentially, they are seldom spheres, they are seldom spheres, but they can be classified as rounded, irregular or crushed, as we have seen. Natural aggregates are not spheres. So, other altogether aggregates can be classified as rounded, irregular or crushed, rounded, irregular or crushed, right. Okay. The shape can be defined in terms of angularity factor, that is ratio of specific surface of size group to that of spheres having minimal volume diameter, that is mean of sieve opening, all right, mean of sieve opening. Let us see what this is. So, shape, as we have seen the shape, and we have also observed that, we have just noted that shape has got an important role, because packing depends upon the shape, and quantifying the shape we have seen. We might be using this concept sometime later on, right. So, shape is an important issue, and angularity factor can be used to define, quantify shapes. Higher the angularity factor, more is the void. For sphere, the angularity factor is 1. Now, let us look at surface texture. The surface texture is related to degree to which particle surface are polished, dull or smooth or rough. Now, this is also important again, because if it is it is important, because surface structure, the bond of the cement paste with the aggregate depends upon this surface texture. The bond of the aggregate with cement paste depends upon surface structure. That is why surface texture is important, all right. Now, it depends upon actually hardness of the grain and the size of the grain and porosity of parent rock. A porous rock always will have honeycombed surface structure. Hard, dense, fine grained rocks generally have smooth fractured surface. Hard, dense, fine grained rocks. So, it is dependent upon the rock type. If it is a hard rock and fine grained, generally have smooth fractured surfaces, because fine grain will go away, but it is hard, not many can go away. So, therefore, you are likely to have generally smooth surfaces. The classification related to this is something like this. For example, glassy is conchoidal fracture, black flint is an example. Smooth is water on fracture of laminated rocks, that results in water on. So, this gravels are like that. Granular, fracture with granular surface texture we are talking about, that means grains will be protruding out. Fracture with uniform rounded grains, sandstone. Rough fracture of fine grained rock, basalt, limestone, etc. And honeycomb structure, honeycombed surface texture come from porous rocks, such as if you take brick for example. So, visible pores and cavities will be there. So, this is surface structure, an important property related to concrete. So, size, shape, surface texture, this is important properties. So, that is what we have looked into today, the size, shape and surface texture, that is what we looked into today. Now, packing characteristics depends on both size and shape. This is what we will look into in the next class. Size, if you have a single sized particle, they will always create some amount of void, you can't reduce it beyond a point, and the amount of voids is a function of the packing characteristics. For example, if we consider simple cubic packing, then the voids here would depend upon packing, but I can assume a second kind of packing, let us say, and you can see depending upon the packing, another particle coming here, voids have reduced, voids have reduced. This is a 2-dimensional picture and you have to extend this idea to 3 dimension. So, packing governs the void content, and in fact, if I have a single sized particle, the maximum packing that I will obtain or maximum packing density that I will obtain, we will define maximum density later on. Maximum packing density that I will obtain will depend upon the nature of packing. This is of course for spherical particle. If you take angular particle, so particle all other factors remaining constant, let us say, void in the aggregate is a function, void in the aggregate is a function of the packing characteristics. For example, this is simple cubic packing, I have larger void compared to this sort of packing, right. So, we have different kind of packings like body centered, face centered, etcetera, etcetera. We will discuss about them. So, it depends upon packing. Now, if I want to reduce this void, then if I want to reduce this void, then what shall I do is I put a small aggregate here and small aggregate here, and smaller aggregates can small sized aggregate can reduce this void. Single sized particle, the amount of void, the amount of void reduction that is possible is limited. You can't reduce the void beyond a point, it depends upon packing. Only when you have different sizes particle or at least 2 different size particle, the void content will reduce. And you want to reduce this void further, let us say, then you use maybe a third finer particle. So, if you put finer particle, they will go into the interstices of this particle itself and reduce the void. So, therefore, void contents depend upon packing characteristics, shape of course, is also a function, but for given shape, given type of packing, number of particles or size distribution of the particle governs the packing characteristics. So, individual sizes we define in terms of sieves, of course, we have seen, but we did not talk of different sizes mixed together, right. So, when you mix different sizes together, then only there is a possibility of reducing down the voids. So, we define a term called packing density, and it is the volume of solid divided by total volume, volume of solid by total volume. So, it is the volume fraction, So, packing density is volume of solid by total volume, and this packing density increases with number with a larger size distribution. Packing density increases with larger size distribution, and this is what we will look into in the next class, the issue of packing density, how particle packs. We have seen that how shape governs. So, to summarize everything today, we have looked into petrographic classes. We really did not go by any code or anything, but petrographic classes are essentially the classes based on mineralogical composition. Their importance lies in the fact that some of those aggregates may not be inert based on their mineralogical composition. Of course, mineralogical composition or parent rock type governs also the shape, because rounded aggregates, it depends upon their grain structure and of course, hardness of the parent rock. So, petrographic classes are important from that point of view. Then we have looked into the size, how do you define them, but the influence of size, how it is important in concrete, that you did not look into, and what are the shape and texture, that is what we looked into. So, in the next class we will look into the how they are relevant. Shape, of course, we have relevant, we have already mentioned that packing would be better with rounded shape, and we will look into the issue of size and their relevance in concrete. One important thing is it is relevant in concrete because better the packing, less paste I will require. So, rounded aggregates is likely to require less paste. Shape is important, structures texture is important from bond with the cement paste. Surface texture is important from the point of view of bond with the cement paste. So, shape is important, petrography is important, and size distribution is important, which we will look in the next class. And I think with that we can summarize this lecture. Thank you very much for being patient. Thanks.